In the AI era, software needs to be faster, stronger, and more secure than ever before. And knowing the right architecture makes all the difference.
Here to share what's coming next in a high-performance and secure software is Dániel Kiss, Director of Software Architecture and Distinguished Engineer at ARM. Please welcome Dániel with his talk, Architecture Features You Need for the Next Generation of Software. Dániel?
Thank you. Okay. Thank you. I have a slide for everyone. I'm Dániel Kiss from ARM. First slide is for the lawyers. The next slide will be for technical people. And if you don't know who is ARM, do you know? No? Okay. ARM is a IP company. We're developing architecture and IPs for CPUs and systems. What that means? We are creating processors that runs 99% of your phones. And you can find our technology from very small battery-powered things towards up to supercomputers everywhere. Beginning of this year, we counted, we have shipped 325 billion devices with our technology. It's quite a lot of them. So the nice thing about ARM, we have an office here in Budapest. 250 people, mostly engineers, on hardware, front-end design and verification, and some in software. That's where I come from. And we are working on these new shiny technologies that I'm going to talk about you. Some of them already shipping in products. Some of them will ship in products in the next years. It's really depending on who is your vendor. Because we are not creating any of this. We are creating the IPs, and we are licensing them to partners that are creating actually products out of them. And you can find our stuff everywhere. AI. Everyone talks about AI all the day. And one of the main concerns about AI is it will eat up all the power that we have, or more. Except, I'm going to show you something cool. We are creating this technology to save power. You will see an animation on the screen. One side is fully rendered. The other side is only rendered with 25% of the pixels. The rest of the pixels is reconstructed by AI, running on the GPU. And the total pipeline is using way less energy than the full rendering. Try to steal the picture, you will not see a difference. The difference is barely measurable, but it's not observable by humans. And this is one of my favorite technologies that we are creating. Because this one really shows something we can create, thinking outside of the box, how we can combine neural engines with our existing technologies and create something that gives us more with less power. And also you can use the same technology for many other fancy stuff. So you can go there, check out, and you can start playing with this. That's a really cool one. But speaking of performance, we really need to think about how we can use and utilize all of the performance that is available in the hardware. You may not know, but we have introduced ARMv9, the new version of the architecture, major revision a few years ago. And we started to add new technology to it. That's called scalable vector extension. Scalable means your vector width is not fixed. It can grow as the CPU is getting bigger, faster, and so on. But you only need to write your code once, because the instruction set helps you to write it once and run on different vector lengths. If you are writing high-performance code, that matters a lot, how wide your vectors, how fast you can process multiple data at the same time. But if you have to rewrite your code each and every time when the architecture changes or the CPU changes below you, then that's a problem. And you can do that with the scalable one. Write once, write on whatever hardware you have. The other extensions that really matters these days is the scalable matrix extension. In compared to vectors, it can work with matrices. So the CPU can do a matrix operation. You can multiply vectors, and you can get back a vector, matrix, and then do rest of the thing with that. And matrices are important and for what? Sorry, yeah, AI, yeah. So deal with that. Programming, that is not easy. But we are creating libraries for you that you can use and exploit them. We are call them Clady libraries. We have a bunch of them, mostly integrated with all the favorite AI frameworks, so you don't need to do that. They are mostly integrated. If not, then talk to us, because that's strange. And you can just use them. Just be ensured if you are running on ARM, using AI frameworks, be sure that you enable these libraries if they are not enabled by default on your distro or whatever platform. So the Clady AI library accelerates whatever AI frameworks really want to do on the CPU, or the calculations and matrix multiplications. And these libraries handle the hardware as well for you. So you don't need to worry about, I have Neon just, or SME, or SV, or what versions. These libraries support, at the same time, multiple versions of the architecture. The Clady CV does all the graphical and computer vision related things, and you can create, and partners are shipping with these technologies, very fancy camera filters and all of that, that you can use it on your phone even today. And you may even use them, just you don't know about it. And my colleague is going to kill me if I don't mention in this building, we have a radio access library that is actually designed to accelerate 5G networks and such. You can check it out. At ARM, we love open source. All of our libraries are open source, so you can just download. It has a very permissive license. You can use it and train your LLM on it, how to write good code, and so on. And that was the easy part. New shiny hardware, get the right library, utilize it, go on. Let's do the harder part. Security. It's a way more harder topic than performance. The first one is going to be the most problematic one. We have a bunch of security topics. I'm not going to cover all of them here. You can find guides and descriptions on the website and so on. But I want to talk about those that really matters for application developers, system developers. The first one will be memory safety. If you not yet heard about memory safety problems in software development, then where are you? So, what's the memory safety problem if you are not a software developer? If you are using the memory where we store variables and data and such in a wrong way, you are writing somewhere you shouldn't write, or using some memory that you shouldn't use. The memory is provided by the hardware, and the hardware here is here to help you to find these problems. We have an extension that is called memory tagging extension. That one works in a way that can detect memory vulnerability problems. How it works? So in a 64-bit system, we have quite a lot of bits in the pointers, but actually we are not using 64-bit physical addresses because that's lots of memory. Usual systems using 32 to 52 bits from that to address the physical memory. We have a feature that is called top byte ignore that ignores the top byte of the pointer. And there we store something that is called tag. 4 bits that describes a given value for that pointer. And the hardware is going to check the corresponding bit in the physical memory. How it works? You have an address that's resolved. We are going out to the physical memory. We are getting the data that you wanted or writing the data that you wanted to write. And then we are fetching the corresponding 4 bits for that. We're comparing with the same thing that is in the pointer. If there is a mismatch, then you have a memory issue. How this works, it's complicated. Not that much, because if you are using an allocator, and you are using an allocator somewhere, probably from the libc, then the libc does this for you. If you ask the allocator, give me some memory, it goes to the kernel, it allocates a tagged memory, it returns to you, it tags the pointer, this is your tag for that allocation, and after that you can just use that new pointer as usual. You don't even need to recompile your program. It will work or crash if you have some problems. If you want to tag everything on the stack, then you have to recompile, but the compiler will do this tagging for you. Let's go forward. Someone would ask from the audience, why just 4 bits? 4 bits is enough. No, it's not. It helps you to detect the problem. If you're testing at scale, then you probably detect all of your problems. Allocators are smart. They are using those 4 bits in a way that is ensures that you're going to find the problem. But if you have an attacker, a really motivated one, then they can go around this. So control for integrity describes what we really want to achieve with our program. Because I have a sad news for you, all of your programs are full of gadgets. Gadgets are small code sequences, a few instructions that if I put together in a certain way, then I can make the program do something that you never intended to do. And the control for integrity is the way to ensure your program is only doing what you are intended to do with your program. We're calling forward edge protection if we are calling a function or jumping somewhere, the backward edge when the function returns. We have software tools for this, for ages. With Clang, you can compile and enable many of these sanitizers and protections. But those will slow your program down and make them bigger, and it's not really for production. But the hardware is here to help. We have a pointer authentication feature in the course. The pointer authentication gives us a capability to sign a pointer and authenticate a pointer cryptographically. How it works first. If you call a function, it always gets a return address where it needs to return. And this one is a pretty good target to attack, because if I can alter that, then your program will return somewhere else I wanted. No one wants that. The first thing, if I call a function, the function signs its return address and then stores it to the stack. Then you cannot modify that on the stack. Before the function returns, it authenticates the return address and then returns. If the authentication fails, your program crashes and you are safe. Very quickly, how it works, the architecture gives you 5 keys. These keys are not visible to the user space, so you are safe. And you have modifiers, so you can increase the key space. So you have a bunch of keys, bunch of ways to sign a pointer and authenticate. We have a cryptographically secure authentication method that produces the signature. If you are signing something, then you attach this signature to the pointer. And if you're authenticated, you just comparing it. It's not that hard to use because there is only one flag to the compilers to emit this protection, and then you are good. And what happens if your CPU is not supporting that instruction? We have a way to do that, because some of these instructions actually encoded in the knob space, which means no operation. And that space is really reserved from the beginning of the architecture. Those instructions are available and do nothing if you are not supporting that feature that is present there. If your CPU is new enough, then it will do the right thing. If old enough, then it will do nothing. And you can ship your same binary on all of your devices. And this one is actually happening today. All of your Chrome browser is protected like that. That was mostly about return-oriented programming. Let's see at jump-oriented programming when we are attacking the forward edge. This is a more advanced technique and more harder to protect against it, because you really need to know where you want to go and it's the right place. If I'm an attacker, I want to go in a place in your function that you don't want me to go, because I want to, for example, jump after the checks that you're performing in a function. I just want to jump to the return part where you return, license check is okay, or such. The architecture gives you a new instruction that is called branch target identification, or landing pads as we call. The landing pads identify where you intended to jump or call, where you want to go. Usually beginning of the function. This is where you want to go. We're adding these instructions there and telling to the CPU, accept jumps and calls only if the next instruction supports this. It works like that. Once you execute any jump or call instruction in this, then it sets a bit in the B type of the processor state. And once the next instruction sees, oh, this byte is set, then, okay, let's check what is my landing pad. And if the two is not matching, then you have a problem. And you usually crash. You get an exception, and up to the application to handle it. It works together with the POUT, the pointer authentication. So you only need to use one set of instructions. For example, your pointer authentication instructions, some of them are actually landing pads as well. So you only increase the function size with 2 instructions if you use both of the protections. This one is controllable by page table entries. Page table says this page is protected or not protected by this. So you can mix up old and legacy code with new one, but the old one will not have the protection, but everything will work. And that was the easy part, because so far we had to use the right libraries, use the right compiler tracks, and we are much faster and safer. And here we come the system architecture, where we are going to change a lot of things. So far, if you look at your pocket, you have trust zone in all of your phones. A trust zone is a secure execution mode of the CPU. The very same CPU that runs your favorite operating system and, for example, Android, then it will not have access to your biometric data. It will not have access to secure peripherals. It will not have access to the DRM content that you are playing, only the secure side. The secure side is segregated by the firmware. At boot time, it sets this memory, these peripherals. It's locked down. It's only accessible for the secure side. And the secure side's software is a locked down blob from the vendor that ensures, okay, these functionalities good enough, secure enough, controlled enough, that after boot, those are locked down there. And this is why we can trust in our devices. Because if you want to buy something and you really have to, for example, click on a button, that button is not accessible by the main operating system, whatever you do with that. The hardware doesn't allow you to check that status. That really goes to the secure side. Secure side handles it, even signs it with the boot certificate and so on, and then let the other side to know, okay, we are good. The user really pressed that button. And it works with many other things. And we are shipping this for ages. But there is one very big problem with that. You cannot access it. You cannot extend it. And that's why we created something else. This is called Realm Management Extension. We wanted to give third parties a way to do similar things. And the similar things means we wanted to create, for example, virtual machines that controllable and secure in a similar way. This extension adds a new way to the CPU, a new mode that we call RAM. And the RAMs actually could contain a VM, for example. Let's go with that example. The RAM extension ensures if something is inside the VM, then it stays inside the VM. Your hypervisor is still able to manage the scheduling and the memory that is assigned to the VM, but the content of it is not accessible by the VM or the hypervisor. The VM can access it. By that, you can create a confidential compute environment when you can compute something, and that execution is really only belongs to that realm. Who is using cloud? Okay. Do we know what the cloud is? Someone else's computer. Okay. With that, you can create something there, and you can ensure that what you loaded there stays there. It works like that. You launch an empty VM. From the VM, you create a secure connection to your server. You ask for the certificate that is provided by the firmware stack that verifies my hardware is the right one, it's secure. It's loaded the right binaries and firmwares and so on. You can verify that signature cryptographically. And then once you are sure this device is a legit device with the legit software, then you load those, your secrets there through a secure connection, and they stay there. The fancy stuff with that, we have an extension also to encrypt whatever you write to the memories also stays encrypted all the time. And it's bind to the given realm. So you cannot even move it to somewhere else because those will be encrypted by a device-specific, RAM-specific key that will not able to leave the silicon. One thing for this, if you are designing your new system, you need to start thinking about how to use such a technology. Because if you just shove everything that you have into a RAM, then you have a huge attack surface that's just in a RAM. You may not achieve too much security with that. I'm just conscious about the time. How it works in the hardware, if someone interested in it, we're adding an additional layer of page tables, and the last level of the page table is the granule protection table that actually ensures whatever access is happening in a system has the right permission to do that. So even if your secure side tries to access something that belongs to the realm, will be caught by the hardware and nothing will happen except some fault. I think we have talked about all of this so far, and I think the next thing that I want to talk about you is a new extension that we announced 2 weeks ago, and that is called Permission Overlay Extension. So far in your application today, if you have a page full of data, all of your application, all of your threads, everything has the same permission. That means if you one of your threads want to write to it, then it can write to it or read it and so on. It's quite a big of a problem if you're running something big and complex, like your browser, your credentials in it, and so on. And you don't really have a tool to fix this, except creating a bunch of processes and then communicating between them and you getting a very complicated system. With the permission overlays, we're giving you a tool to create a different view of the memory from the same application, spatially and temporally. Let me show you an example. I think it helps you to understand this a bit better. You have 2 code pieces in your application, code 1 and 2, and you have 1 piece of data. The base permissions that is provided as of today, read-write, and those will not change. But we are adding additional layer top of that, and data protection overlay will give you different writes for those segments. One of them will have read-write. The other one will only have read access as you configure this. All of this configuration is done inside the kernel, so user space can directly write into these configurations. These are big memory tables that need to be configured through a simple kernel interface, and then the hardware ensures all of this. So this is checked by the hardware. How this is really done in the hardware back then, once you execute a piece of code, we look up your page table entry, then we get an ID. Also, we have a temporal ID that is inside the processor state. With these two, we look up who you are, what you are executing, and based on that, we look up the data permissions that you will have for the given address that you are trying to access, and also look up the special permissions. Execute permissions, for example. Do you have right to execute what you are executing? And also, we have additional fine-grained controls. Does this code have right to execute syscalls or special instructions? So we can lock down things. What we could build from this? In this example, let's build a browser. And in a browser, you have JavaScript. As a kid, one of the first things that I thought, what should I do and what I shouldn't do? Don't download random software from the internet. As of today, everyone runs JavaScript. So with JavaScript, one of the problems, we compile things on the fly, and for that, you need a piece of code that can read, write, and execute the same address. We do many things to prevent this, because that's wrong, because if I can write there, I can write my software there, and if I'm an attacker, I just write whatever I want to execute, and I just do that. And it's happening. With this, we can create a special region in the code that is actually the JavaScript compiler that can write to the output. We only give execute write for the JITted output, so your JavaScript that does the fancy stuff in the website only able to execute itself. It will not able to write itself. It will not able to read from locations in the browser that it shouldn't read, and only able to jump to certain locations that it needs to jump and not nowhere else. Also, we can revoke syscall permissions from it. It shall not able to do syscalls. There is no scenario when it needs to do a syscall and ask the kernel to map additional memories and so on. Okay. And at ARM, we are really like open sourcing things. And also, we are also using AI for many things. And this is, speaking of security, I have to mention, we open source a tool that actually helps you to do security testing. It contextualizes all of the security checks for you. It really improves the way you can assess the software security. Take a look, it's really cool. We are using internally as well, so give it a go. And I think and we are hiring if you can. Okay, thanks so much for your attention, and I'm really happy to answer your questions as well. I was just speaking to Dine.
Any questions in the room? Oh, okay.
My question is related to your security tool, which is you are saying that it is context aware.
Yep.
So how does it makes its context, and is there any way that it keeps updating its context, because we have new vulnerabilities, and let's say for those assessing those vulnerabilities, we have new plugins. So how does that happen?
It's pretty complicated.
Just
we have a,
just at a block level, if
so
you can.
it's also based on LLMs and regs, and it can update itself, and you can load more context to it. You can load your complete code base to it, and then let it run. Also, you can load more stuff to it, like documentation and use cases and so on. So it sees, it's not only a static analyzer that looks at a given line of code. It looks at the context of that line of code, understanding how it is used. You can filter out a bunch of things that it's not relevant for that line of code, but also it may brings you more things. Okay, this is more relevant for you here.
Yes, I agree, and I can understand, because sometimes some of the tools, they just read a library. This library is being used, and they know that this library has this CVE, they just publish it. But if you look a little bit deeper, you find out that this CVE can only be exploited under these circumstances, and those circumstances in our application would never happen. So it's a false alarm.
Something like that.
Okay, thank you, thanks.
It uses a bunch of fancy technology behind it.
Thank you. Any other questions in the room?
My question is about prompt injection threats. Is it working for that? When the user use prompts to try to hijack or hack the system, does your architecture work for that kind of threats?
Yes. It really depends on what you are trying to achieve. If your attacker is, doing something wrong with the buffers, then MT can help you. If you want to keep your stuff secure, then you want to use RME. If you want to segregate your program to, compartmentalize it internally, then you use PoE2. And you can use a combination of these, depending what you really need.
All right. Any more
Hope I
questions?
answered the question.
Okay.
Maybe regarding the same topic, because you said that's an AI-powered tool. Do you?
This one, yeah.
Yeah. Do you train your own model locally, or use just public BI models? Because public models, they have known vulnerabilities basically. So, with the prompt injection, there was this case in which that some guy passed some data to a GitHub. He posted there, and a couple of months later, models were trained on public data. So he got his backdoors already injected in the training data unintentionally. So.
Yeah, that's our private.
Mm-hmm. Okay.
So we care deeply. We are an IP company. Our value is on our IP, so we are very strongly protect what we are doing.
All right. One more question, maybe.
Cutting out, I would like the X factor of the AI. What do you think?
The X factor of the AI, according to your opinion.
It's a pretty good tool. It's not evil. We are evil, and the attackers are using it, for example, to attack more and more. So that's why the security matters more. But as you see, we can do fancy stuff with that as well. It's just a new tool. It's pretty handy new tool. Depends on how you use it.
All right. Thank you very much, Dániel.
Thank you.